get started?
Sure.
So, okay. So welcome to our GPC seminar series. And it's my great honor to introduce Dr. John Wettlaufer. So it's really a lot of things to mention, but I will try to keep this short. So Professor Wettlaufer is the Bateman Professor of Physics, Mathematics, and Geophysics at Yale University, and a research professor at the Nordic Institute for Theoretical Physics. He was trained as a condensed matter theorist, and over the years has branched out substantially across many disciplines and draw together new approaches using tools from applied math and statistical physics to understand complex systems with broad-ranging applications from sea ice, fluids, climate, to astrophysics. So particularly relevant to our GPC seminar series, Professor Wettlaufer was the chair of APS GPC and has been a strong advocate for bridging the physics and climate communities. So with a note he published in Physical Review Letters in 2016 entitled Climate Science and Invitation for Physicists, he highlighted many opportunities in this area using tools developed by physicists. And finally, John is also a member of the Nobel Committee for Physics. So as we know, one of the 2021 Physics Prize was focused on the Earth's climate. And if you have not done so, I strongly recommend watching the inspiring Nobel Prize presentation given by John. So I'll put a link in the Zoom chat. And with that, I want to thank John again for being our speaker today. And please feel free to take it away.
Great. So thank you very much, Yao and Pedram and GPC, which, as Yao mentioned, I have a history with. And I'm glad to see that it is continuing on after the initial struggles, as it were. So I'm not, of course, sure who's in the audience and what their backgrounds are. So what I want to do is to provide a rather broad landscape for the question posed in the title here, and then give you a comparison and contrast between the approaches, the traditional approach and what I would call, I guess, the less traditional, although still seriously embedded in the history of the topic, that approach. And then I will take you through how we've generalized and solved a very old problem to make predictions with a rather simple approach. Okay. And if I don't know if Pedram will field questions, you can interrupt me at any time also. Okay. Now, as we were talking about before, when people study many geophysical phenomena, the origins of the studies tend to be the origins of exploration. That is, that the science emerged out of the exploration, and the exploration really always has this drama, as described here by Kriegel. You know, that you must overcome insurmountable obstacles in the shape of mountains of ice that keep piling up. The Lord alone is with you. And this kind of drama, of course, is if you're walking around watching and listening to the deformation of the ice pack, it has to influence you. The question is, what can you understand following the exploration? And what I want to do is tell you a key part of history in this particular area. Okay. And this has to do with these two gentlemen, Weitprecht and Peyer, who were both military men. One was in the army, Peyer, and Weitprecht was a naval captain or commander in the erstwhile Austrian Navy. At the time, of course, there was not much that a Navy officer in the Austrian Navy could do to make a name for themselves. And so the natural thing was to do some exploration. And these two people organized and set out on the well-known 1872 to 1874 Austro-Hungarian North Pole expedition. And here is a picture of their ship frozen into the ice. Now, they discovered what we now call Franz Josef Land by getting stuck there. And they had the foresight and the insight to make measurements of the ice thickness and the surface temperature as a function of time while they were stranded. They were such ardent supporters of the idea of doing systematic measurements in the field that their efforts led to the first international polar year, 1882-1883, which was a realization of this, although unfortunately Weiprecht, who was the main campaigner, never saw that happen. Now, to convert it to science, Weiprecht came to the University of Vienna and approached Stefan. And so you know Stefan from the Stefan Boltzmann law. He measured empirically the equation that you're all familiar with, and it was his student Boltzmann who derived the proportionality constant from statistical mechanics, which he was largely responsible for developing as well. And as we also know, the prominent role of the Stefan Boltzmann law in controlling the surface temperature is key, not just in the polar regions, but everywhere. So in the time-honored tradition of science, Stefan sat on the data. And it took quite some time until he could put it in that data and other data into a context. And so it's this first paper that is bringing together a bunch of field data, not just that from Weiprecht to Peyer, to develop the idea shown here of how ice grows when the surface temperature gets cold. So here's a layer of ice of thickness h. There's a temperature drop delta T over it, and the latent heat generated at the interface is conducted through the ice and off to space. And that simple and interesting relationship gives you this square root of time growth of the ice thickness. So when people talk about the Stefan problem, it's a general class of problems that are moving boundary problems, but it was actually originally motivated by observations made in the field. And he looked at the simple problem where the underlying ocean, as it were, was isothermal. Okay. As we will come to in a little bit, there is another contribution to the balance there, and that is the heat flux from the ocean to the ice, which can have a controlling influence on the fate of the ice cover. So this is a very interesting example of translating, simplifying, distilling complex field measurements into a simple model, which has been shown to be valid since its inception. Now, of course, you can explore the Arctic without going there, and we have daily satellite information, particularly of the polar regions. You can find this on the NSIDC website. This is just from a few days ago, looking at the ice cover from space. And this has been the mode, or a mode of observing the ice pack since about 1979, the beginning of the satellite era. And so the luster of going and to the Arctic or the Antarctic is replaced a bit by the downloading of satellite information. The question that we are interested in is, what's the fate of the system? And you could see here, I'm plotting the extent of the ice cover in millions of square kilometers as a function of time in the season and over time. And what you see here is that the system is oscillating. As there's a maximum, there's a minimum. It's been doing this for, as far as we know, for about 1.5 million years, going through the seasonal cycle. And the question of the fate of sea ice really has to do with this minimum, which is the minimum was 2012, and you see there in the blue curve just this year. And people, of course, are worried about when this minimum goes through zero. Okay, and can that be predicted? Because we know that the Arctic is a bellwether for climate change through Arctic amplification, and we really would like to understand when and if this minimum will go through zero. Another way to look at it is shown here also from NSIDC. You know, if you extrapolate this, does it go through zero? The axis here is 5 to 10. But does it go through zero in 2030, 2050, 2060? And that is the $64,000 question, or 64 million or billion dollar question, depending on how grievous you think that transformation will be. Okay. Now, of course, if you're just giving data and you extrapolate, that's a problem, right? You want to know what the mechanism is. If we were plotting the 100-meter sprint times as a function of time, you know, for the Olympic runners, that eventually, you know, they would go faster than the speed of light, then they would violate causality, you know. So extrapolation is dangerous, and that yet we either extrapolate or we try to predict with models. And the underbelly of the problem has to do with, typically thought to do with the ice albedo feedback. And so here you see a mosaic of the ice pack, and you see that, you know, open water is dark, has an albedo of about 0.2. The thicker ice is got an albedo of about 0.65, and then there's everything in between. And so you could see in one image the variation of albedo, and that is key in the energy balance. So the thinking is not so different than the original Boudico-Sellers idea, right? That you have a slight change in the areal fraction of the ice cover that absorbs more incoming radiation, which heats the system, ablates back the ice, and there could be a saddle node bifurcation shown as a cartoon here. Now, scientifically, we would like to know whether there is hysteresis. Practically speaking, whether there is hysteresis or whether there's just an abrupt change is probably 6 of 1, half dozen of the other for humanity's purpose. If the ice cover vanishes for some part of the season, it may have substantial influences regardless of whether it's reversible or irreversible. But that fraction of the ice cover that is open water is a key component of trying to understand the mechanism of the ice albedo feedback. Okay. So there are generally these 3 approaches. 2 are more popular than the third one. So we have observations that are rather low resolution, paleoclimate data going back quite some time. We have, as I've shown you, high resolution satellite data on decadal timescales. And we have climate models. And then we have what I would call observationally informed theory. And it's an unsurprising claim coming from myself that I believe that many of the methods that we use in statistical mechanics and dynamical systems, et cetera, inform all of these areas, in fact. But I'm just going to focus on our part of the work on the number 3 after I go through the 2 general approaches. Now, Of course, the emergence of modern climate models is really commensurate with the emergence of trying to understand how one predicts the weather. And wonderfully, now we can look here at about the tropopause. This is the moisture at about the tropopause, and you can watch all the features that you're familiar with understanding if you take a course in geophysical fluid dynamics. You have intertropical convergence zone here. You have the jet stream, and many, many other features, which you can observe from the comfort of your office. And then you can actually go to the laboratory and study these things with a rotating table. And the general conclusion is that we can view geophysical fluid dynamics as a laboratory science. That is, we really do know the equations of motion, and we can study features in the laboratory that reveal themselves quantitatively and of course qualitatively in the atmosphere and the ocean. And the typical laboratory theory numerical simulation dichotomy exists in atmospheric and oceanic flows, with the usual caveats about how we numerically resolve various things. Now, if we think about the ice pack, and now I just invite you to observe what's happening here and ask yourself, is this material that's floating on the surface of the Arctic Ocean a couple of meters, is it a fluid? Is it a solid? Is it a granular material? What is it? And so there was the minimum. Now it's growing back the maximum. This is 2012. So then the question is, in analogy with a rotating table in the lab, we would like to quantify the geophysical scale evolution of the system, but is there something that has parity with the rotating table? And I would say the answer is no. That to try to get the mosaic correctly reproduced or predicting the major features is very, very challenging in the modality that we can make progress with geophysical fluid flows. Okay. But this is an important geophysical fluid flow. It's just not a fluid. Okay. And that's the challenge. Okay. So in the spirit of weather forecasting and therefore climate modeling, the conservation laws can be written down, and they've been understood for a very long time. And I just want to focus your attention here on the momentum balance, right? So you have accelerations, you've got wind stress, you've got air stress, you've got the Coriolis effect, you've got sea surface tilt, you've got pressure gradients. And now I'll highlight this red term here, div dot sigma. So if there was only the red term, div dot sigma, so all the black terms were zero, div dot sigma 0, that's Stokes flow. Okay, and we can understand that for Newtonian viscous fluid quite well. But for the ice pack, we need to be able to relate the stress and the strain rate. That is, we need a constitutive law for this random discontinuous material. And that is the limiting issue, or a key limiting issue, in predicting the fate of the system with such an equation. And such an equation is, of course, a component of every climate model in one variant or another. Okay. So we really would like to know what the constitutive relation is and how it's related to the ice thickness, and how could we make a predictive model of it. And so since you can't obviously start and look down on this material and write down something that is coherent, although people do, I would say rationalize it, there is the reductionist approach, which the first practitioners or people interested in the problem took, and that is, can you understand what goes on just from the individual interactions between flows. Okay, this picture beautifully highlights the multiple scales. You have these little ice flows in their early birth, and you have a wave field going through this, and you can ask on what length scale is this system differentiable, for example. Now, in 1975, Drew Rothrock wrote this: if we knew what the constitutive equation for pack ice should be, we would not need to pay attention to the mechanisms of flow interaction. But the simple fact is that we are not at all sure about the constitutive equation, and thus we've turned to the study of these mechanisms: rafting, ridging, shearing, and opening, so one could deduce what one can about the large-scale behavior of the pack ice. Okay, so that's in 1975, and it took some time. In 2008, Dominic Vella and I could use the basic theory of the mechanics of elastica to divine and predict quantitatively this regime diagram, which just shows you the major deformation features in the ice pack. That is, we could predict these with a basic theory of the elastic properties of the material, and yet still, given this, how can I tell you on a large scale where there's going to be a ridge, where there's going to be a raft, and so forth? So building up a picture still in the spirit of what Rothrock was intimating is at least out of our reach, or has not been possible, given what we know about the basic mechanical deformation features in the ice pack. So I go back to this and say, well, we don't really have a fundamental understanding of the constitutive relation, right? Like we might do with a continuous material, like even a non-Newtonian fluid. We have lots of information because it's a continuous differentiable material. So we still have this question: what's the dependence of stress on the thickness and its distribution, and what are the consequences for modeling? And so now we could imagine, and this is what is done, choosing a constitutive relation of some sort, elastic plastic, viscous plastic, and so forth, which is done. And what are the consequences for our ability to predict the fate of the ice pack in the future? And so I just want to make 2 points here, and point you to the recent IPCC AR6 report in chapter 9, and I'm just quoting the conclusion here. This paragraph is: the CMIP5 models and reanalysis failed to capture the observed distribution and evolution of Arctic sea ice. Most CMIP6 models do not capture the observed spatial distribution of sea ice thickness realistically, and this leads to a low confidence in the estimates of thickness from reanalysis and CMIP5, CMIP6 models and the projections of sea ice volume. And then in terms of what we're observing with a rapid decline, like I showed you, Ian Eisenman and his student studied that, and they found that the simulated rate would be captured only less than 1% of the time in these models. Okay. And moreover, they found that there's the observed asymmetry that we find from satellite information, retrievals on Arctic and Antarctic sea ice, is not captured. And so if things are modeled correctly or consistent with observations, they could be for the wrong reasons. And of course, we could look at figures and so forth, but the idea is to try to predict when the ice may or may not go away. And it appears that a major method that we use gives very low confidence predictions. Okay, so the momentum equation has this particular issue of trying to understand what the right constitutive law is. At the same time, the same individuals in the same group, 1975, they took a different approach. They were at once trying to make a model, the Ajax model for the momentum equation and the constitutive law, but they also said, let's abandon that and let's try to look at the mosaic in a different way. And they derived this theory of the ice thickness distribution, which I do want to make the following point about. It has been an organizing principle for how one does look at climate model output. That is, how does one categorize the thicknesses? How many bins of thickness does one have? So it's an organizing principle, but it's not generally used as a predictive theory. And the reason is really the same, but translated into a different component. So that's what I want to now focus on for the rest of the time that I have. Okay, so here's the idea, right? You look down on a region R, and some fraction of that region has ice between thickness H1 and H2. That defines a PDF for the ice. Okay. And so the question is, how does the PDF change in time in this region? Of course, you can bring in ice into the region and advect it out. So that's one way to change the distribution. Of course, depending on the season, the ice could be melting or ablating or growing. So you could change the distribution through the growth rate, which I'm calling F here in their original notation. And then you can deform the ice like we've seen. You can make thicker ice from thinner ice, or you can make thinner ice from thicker ice by divergence. And that's put into a term here for the mechanical interactions. Okay, so we have advection, we have growth and decay, and we have mechanical deformation. And so this gives you, if you will, a large scale view of the probability of finding ice of a given thickness in a given region. But this function here, psi, the mechanical interactions function, they referred to in their paper in the following way. The present theory suffers from a burdensome and arbitrary redistribution function. It's hard to write this kind of thing in a paper anymore, but it's certainly honest, right? That they didn't quite know what to do with this, and that's the problem. That this function here is simply translating the ignorance that we have about the constitutive law and the momentum equation into this theory. Okay, and so one way to think about this intransigence is to imagine that we have a situation just like in Brownian motion. Okay, so here's now, it's not a pollen grain, it's a little ball. The seeds are vibrating, and you notice, right, that there's an overall displacement of the Brownian particle due to the very, very rapid collisions with the underlying seeds. Okay, and the overall displacement, of course, occurs on length and time scales much, much larger than the collision time scale with the small particles. So in the same spirit, we argue that the ice thickness distribution changes slowly relative to the individual mechanical events, the failures, the rafting, the ridging. They happen very, very quickly to change the ice thickness locally, and the distribution changes rather slowly with respect to those time scales. Okay. So once you make that statement, then you can revisit this redistribution function as follows. Okay, so those of you who are familiar with this, of course, you're familiar with this idea, maybe not the ice thickness distribution, but we're viewing this in the same spirit of kinetic theory, where the idea is that there are hops from ice of one thickness to another thickness, and the difference between those transitions from thick to thin and thin to thick, overall possible thicknesses, changes the ice thickness mechanically. Okay, and so I just said in words what this integral is doing, and there are probabilities, transition probabilities of those events occurring. And this is an exact analogy with the master equation for probabilities of collisions with solid molecules with a Brownian particle, like I was alluding to before. Okay. And when one takes that approach, then one can expand the integral using Kramers-Moyal expansion, and one can convert this now integral differential equation into a differential equation, which has these two terms, a drift term and a diffusion term, or we call this the deterministic and the stochastic term. Okay. Where the K's are the moments against the probability, the transition probabilities. Okay. Okay, doing that allows us now to close this theory, which was not possible previously. That is, since psi was not written in the original theory in terms of G, this approach allows us to do that, and those psi becomes these two terms in the box over here. And then I just want to point out that the K1 and the K2 are the first and second moment against the transition probabilities. And the argument that we make is that these are constants. The reason is that the ice doesn't care where it is when it breaks or when it deforms. In the same way, when the Brownian particles in one part of the Petri dish, the collisions with the solvent molecules are the same as in any other part of the Petri dish. And so, of course, boundaries are important, but in the interior of the pack ice, the mechanism of deformation doesn't care about geography. It only cares about the thickness. Okay, so having done that, now we can study this and see how it plays out with respect to what we observe. Okay. So let's just look at the winter, because it's a very clear example. And let's move in a Lagrangian frame, noting that if you look at the ice motion, the ice motion field on the satellite era, you find that it's solenoidal to about 1 part in 10 to the 11. And so we could rewrite this in a Lagrangian frame and then look for the invariant measure or the steady solution in winter. And to do that, we appeal back to Stefan. That is that the growth rate F is just dH dt in this notation. And so thin ice grows faster than thick ice. And just putting in this F into the blue box, and we can write down an analytical solution here. And it has only two parameters, which is good because we have bivariate data. And so that's this solution shown in the box here. And when we compare this to the ICESat data, this is what we find. Okay, so we have bivariate data. The satellite data is the red circles, and our curve for the winter is given by this function here. And I just want you to observe that when the ice is thin, both mechanics and thermodynamics give rise to its deformation. But the only way you can make very thick ice is by mechanical deformation. That's the e to the minus h on h contribution. Okay, and so we have a clear interpretation of the mechanical features that give rise to this distribution, combined with the growth and decay that we are used to thinking about in just 1D column models of ice growth. Okay, and so this is gives one confidence that simply solving this differential equation can capture the aggregate behavior of the ice pack across the entire basin. So now the question is, can we take this to the full season, the full seasonal evolution? Now, let me just go back. Notice, of course, when it's cold in the winter, as soon as open water forms, it freezes. So at the origin, there is no ice. Right? There's a tiny fraction of the area that freezes very, very quickly. But this equation is solved with boundary conditions that G is 0 at the origin and at infinity. But of course, when there's open water, some part of the distribution lives on the origin. And so that's what we try to capture in order to make predictions of the full seasonal evolution. Okay, so now if we write the original equation, which is really now a Fokker-Planck equation in flux form, shown here, and note now that the new norm, instead of just being 0 to infinity is 1, has to include the time rate of change of the area of the open water. Okay, so now we just differentiate that with respect to time, and that relates to the flux difference, and then we can say, well, look, there is an ice thickness below which we cannot distinguish between ice and water. We get that from the optical properties of ice, so it's about 10 centimeters of ice, and that allows us to have a boundary condition at the origin, which is a dynamic boundary condition, and then to proceed to use the whole system to do climatology. We solve this Fokker-Planck equation using the Sempner 3-layer model for ice growth rate. We want to have this because it deals with some of the transient issues associated with snow and so forth. Okay, so now we can do climatology. From the upper left to the lower right, you're going on in time. So you have January, February. That looks like the winter solution I showed you. And then going to the spring, April, May, broadening out. And then once you start to enter summer, in the early part of the summer, you start to see that there is a rollover. The second peak starts to form at the origin. That peak grows in August. And then as soon as it gets cold around now, a couple of months ago, it rolls over again to regain the winter solution. Okay. And so this double peak is a big part of the effort to capture observations. And here's an example from SciSex. That's upward-looking sonar from submarines. And in September of 1993, where you see this double peak appearing, and here we have the same thing occurring in the model, or in the theory, really. The timing of the exact place where the peak starts to appear is controlled in large part due to the heat capacity of the ice and how much snow there is. But the point is that we could reproduce this key feature in the ice pack distribution of the ice thickness. So now, finally, the last few slides I want to go through. We have a PDF, so that means we can compute all quantities, all moments. And here we see the mean thickness, the seasonal cycle of the mean thickness, and the albedo. And so you see that the mean albedo is leading the mean thickness. And so the ice albedo feedback is intimately slaved to the ice thickness. So the thickness is really, really important in getting that feedback correct. Okay. Now, what happens to the open water fraction? Here I'm showing you the curves of open water fraction as a function of the month for 3 examples. And I pointed out at the beginning, this ocean heat flux, that's F sub B, okay? So the lower curve, the black curve, has no ocean heat flux and no additional greenhouse gas forcing. That's what delta F naught is. That's the lowest curve. And you see that the open water fraction is 0 for most of the year, except for in the spring and summer, and then it just drops off when it gets cold. And now as you increase the surface heat balance, that area under that curve increases. But now notice the ocean heat flux. The system is much more sensitive to the ocean heat flux. And here you see that there's a much larger region of the season where there's a finite areal fraction of open water. Now, 25 watts per square meter is large. It's observed, we typically think of the central basin as having 2 watts per square meter, maybe 2 to 5, depending on how you average in time. In the Eastern Arctic and Eurasian Basin, there are large heat fluxes associated with the West Pittsburgh Current. But this is just to show that because of the nature of the Stefan problem, this flux at the bottom is really quite important in controlling the open water fraction. And now you see, if you just change it by 1 watt per square meter, then there's a transition, there's a liftoff. There is no part of the season where there's no open water. And so that's a key aspect of understanding the nature of the ice albedo feedback. Okay. So now I'll just make the comment that you may or may not be aware that to every Fokker-Planck equation, there's a Langevin equation. So there's a duality. You give me one, I can give you the other one. And here it is. In our case, the important thing is that now we have a very simple stochastic differential equation that we can use to look at the ice thickness field as well. And this first term, the drift term, has the possibility of changing sign due to this under ice, the ice ocean heat flux. And so when the ice gets thin, there's a change in the energy balance. The reason we want to look at the Langevin equation is it allows us to peer into why is it that the second peak emerges. And so we can do a simulation here, begin with 10 to the 5 realizations of the winter solution, which we know very well, integrate forward with a very fine time step, and from the winter to the spring, we see that this peak emerges. The second peak emerges. We already saw it by solving the Fokker-Planck equation, but here we can diagnose that it comes from a change in the energy balance when the ice gets thinner, or when a fraction of the distribution gets sufficiently thin. Okay. Great. All right. So to summarize, I would categorize what I've discussed as having 2 features. I dwelled on the first one principally, stochastic successes. So using basic concepts from statistical physics, we developed a theory for the evolution of the sea ice thickness distribution, and we tested that on the largest observational scales on thousands of kilometers. Okay. So either a single PDE or SDE can be used, I think, as I've showed you, to study the climatology of sea ice. I would argue that such an approach would provide a natural ingredient for comprehensive models that could be perhaps tested against a momentum equation, and perhaps be incorporated for predictions. The fact that we have this duality between Fokker-Planck and Langevin allowed us to show that there is, or I'll just state that there's a space-time ergodicity in the ice thickness field. That is that as the transect of the submarine went across the entire basin, the distribution is measured, and it's realizing all parts of the possible state space of the system. Now, I only touched briefly on what I would call elastic successes and failures. On the one hand, we can use the Foppel-von equations to predict the main deformation features in pack ice, which is what I showed you, this regime diagram. But it still begs the question, how could we use that local reductionist mechanical understanding to homogenize and create a reasonable constitutive law for the ice pack? So finally, I want to acknowledge not just the people who fund the work, but the collaborators. Most of what I've spoken to you about today began in part as the thesis of Srikanth Topoladoti and at the GFT Summer School in 2015. And he since went to Oxford and now recently started a position at Leeds. And the mechanics, also GFD, started with Dominic Vella, and Sahil Agarwal and Wusak Moon and Filippo Garnieri have worked on various aspects of things I only touched on and didn't go into great detail on. But in any case, if you're having trouble sleeping, there's plenty of things that I could provide to cure your insomnia. Thank you.
Thank you, John. It's a beautiful talk. And we already have a few questions in the chat. So Pedram, do we just read the questions? Or...
Oh, I could see it. Okay, the first question is, does surface area of ice have no effect whatsoever on ice albedo? Oh, it does. So you have to realize, so two things are happening in the model, right? Or in our prediction. Okay, so key is that the ice thickness is a crucial aspect of the albedo. Think about it. If you, anonymous attendee, have ever walked on lake ice, right? When the ice is just thick enough to walk on or safe enough to walk on, say 15, 20 centimeters, it's dark. When it gets thicker, it becomes white or lighter. So the albedo, right, there's a Beer's extinction coefficient. The albedo definitely depends on thickness. And then since we know the thickness, okay, and we're tracking the area, then we get the area dependence for free, as it were, okay? So we know the area, we know the thickness, and therefore we know the albedo. And you can't really do that, obviously, with a column model. Okay, okay, so Mitch Bushik asks, computing K1 and K2 require transition probabilities between different ice thicknesses and classes. Where did these probabilities come from? And then can they be estimated? Okay, so they were estimated. If you so K1 and K2 are part of the estimation through the fact that we fit the data, right? So there was the solution to G of H. The invariant measure has H to the Q, E to the minus H over big H. That Q and that H have the K1 and the K2 in them. Okay, now. Because we only have one K1 and K2 that fit the data, that is consistent with the ansatz that I made, that the mechanism of deformation doesn't care where it is in the ice pack. Okay, and since the measurements are made across the entire basin, the argument is that K1 and K2 are constant, right? They don't depend on position. Now, that would definitely break down, okay, because as I go to the marginal ice zone, right, or I get to within a region of the boundary where there is a divergence or that there is effect of a coast and so forth. So almost certainly those transition probabilities would depend on orientation, thickness, and position, in a way which is not accounted for in what I've shown.
I guess a quick clarification. So is that what you also see from the data, where if you look at thickness distribution near the ocean, maybe it doesn't follow the theoretical distribution?
Right, but so there's then a problem with the data itself, right? So what I showed you for the winter solution, right? That winter solution is central ice pack, ISAT satellite data. Now, as you get towards the boundary, the assumption of solenoidal velocity field changes. Okay, and so what controls the ice thickness has a very large dynamical component. So I have no test of that, but of course I know that to be true, right? That there will be a divergence. There'll be free drift and things will change near the boundary. Now, also we know, for example, in the Beaufort Gyre, that pushes ice up through the Lincoln Sea and it piles up over in the Canadian archipelago. So there's a persistent wind, and so there will be a long range, interaction in the ice pack, which would change K1 and K2 also. So those things would be something that you could easily put in. We're solving a PDE, but to leading order, this is I would say Occam's razor for the solution. Flow size distribution, we have not treated the ice flows, right? So we simply have treated the fact that there's a distribution of ice thickness. So whether or not that ice of thickness between H1 and H2 is on a flow that's 10 kilometers or 1 kilometer is not part of the picture. So of course that's something people could do. The flow size distribution itself is controlled by the mechanical effects in the redistribution function. Okay, so there's a bit of a chicken and egg issue there. And so would you get an improved, would there be an improved version of the winter solution, if you had included somehow the flow size distribution? I don't know, and I don't think so. But it's certainly the case that people do look into that. So my argument would be, because the mechanical deformation itself redistributes the thickness and the flow size, then you might argue that